How are you guys doing? Good. So before I start and talk about myself, I want to hear a little bit about who my audience is. This is the benefit of not being a conference and being a meetup. So this should be a conversation, and not just me standing up here and talking. If you're silent, then you're just going to hear me talk, and that's all on you. So who, by a show of hands, who in here considers themselves to be a data scientist? Interesting. Okay. So what are the rest of you guys? What category? Are you just software engineer? If you're not a data scientist but consider yourself as just a software engineer. Aspiring software engineer. Oh, aspiring data scientist. Okay. So somebody tell me, who's something other than a software engineer or a data scientist? Analyst, data analyst. Okay. Data architect. What else? BI developer. Statistician. Okay. Anybody else? Any other representation? Any business people? Sales. I think you're in the wrong. I'm just kidding. Just kidding. Sort of. So all right. Well, then I'll tell you a little bit about myself. As she introduced me, I'm the VP of. Actually, this is wrong. I got a promotion. Thanks to me. Good to me. So yeah, this is, I run the analytics group at the weather company, recently acquired by IBM, as you guys may have seen in the news. So our life is very crazy now. This is how you can reach out to me if you'd like. I used to not use Twitter, but I was forced into it. So again, I think she kind of said this, but how did I get into this mess? I'm actually not a data scientist either. I just play one on TV. But I come to this through the big data processing, kind of through the back door, you might say. I got involved in big data by virtue of having a big data problem at my previous startup company, and where traditional data processing and databases did not solve the problem. So that's how I got involved in the Cassandra project very, very early. So again, if you want to know how to break your distributed database, I know a lot about them, and I've broken a lot of them. And if you want to come cross-pollinate and join us at the Atlanta Cassandra Meetup group, be happy to have you. So let's talk about the weather company. So we are at heart a data company. Most people think of us by our brands, the Weather Channel, Weather Underground, WSI. If you're a pilot, you probably know a lot about WSI. If you're not a pilot, then you probably don't know anything about it. But we have a significant business on the data side. That is at heart what we are. And as you can see here, it's a lot of data. We do about 30 billion requests on our API every day. So this is the likes of Apple, Facebook, Yahoo, Google, Samsung. If you get your weather data from them, it's actually coming to our API on the back. So we also have 120 million active mobile users. This is actually the third largest mobile user base in the world, as I have on my nice slide here. So we have all that data. So that's a big number. I'm going to explain that number because it's very hard to even get your head around. So it's not weather data. Weather data is actually a very, very small part of our overall data set. 120 million active mobile users produces a lot of secondary data, a lot of web logs and behavioral data that comes from our apps and our websites and those sorts of things. So the total amount of data that we see run through our networks every day is about 360 petabytes. That's 10 3/4 exabytes. So if you draw that, if you don't know what an exabyte is, you should draw that out on when you get home or on your paper. It's a very, very large number. So we are, without even trying, a big data company. So at the end of the day, the bottom line is most of the weather data that you consume on a daily basis or that you don't consume actively but are the benefit of comes from us. So in terms of this use case for analytics, what you guys care about today, we built a platform that I'm going to talk about in a minute that ingests lots of events. So depending on, this slide is actually slightly old. It can be anywhere from 1.5 million to 2.5 million per second events that we bring into the platform. And so these are all those sort of real-time events that I was talking about, where we capture beacons from our websites, beacons from our mobile apps, those sorts of things. So log data, weather conditions and forecasts, all that kind of stuff comes in. So the problem is we got to keep that data forever. And we want to shorten the cycle from the time that we get that data in to the time we can extract some insight from it. So as you can imagine, the keep data forever, it's not too bad of a problem if you can throw it all away and only pull that data in every day. But the need to keep it forever is a real challenge. So in order to do this, we needed to build a system that would work on both batch and streaming data, right? To be able to do analysis across both, and preferably with a common paradigm. So we have a lot of data scientists at Weather who are embedded in various business units and some who are in my organization. And we had to be able to support self-serve data science and exploration across all those business units. So this is one of our key problem domains, actually, one of our most difficult problems. And we also need to support traditional BI tooling on top of that data. So the meat of this talk is about how we did this, right? So who in this room, just by show of hands, would call yourselves, now maybe not by this scale, but by whatever scale you walked into the room with, you know, who of you would think of yourselves as having big data problems? Okay, so ish, big data-ish. You know, and let's define big data for a second. I'm just curious, like when you want to, and obviously that's an intimidating, right after I said 360 petabytes, nobody wants to speak up, but let's pretend you didn't see that. Like what define big data? Who thinks you have a big data problem?
Hundreds of thousands of hours of audio data.
Okay, yeah, I'd say that's big data. How many, what sort of data in size is that?
I'd say each audio file is probably about 10 to 20 megabytes each, so you can multiply by that.
Okay.
And
anybody else?
you know, recently I analyzed 3 months of audio data from a single customer, and that was about 100 gigabytes.
100 gigabytes. Okay. Yeah.
Seismic data.
Seismic data.
Yes. 1 GB each sensor, 1,000 sensors in one oil rig, several oil rigs. So.
Okay, so a petabyte-ish. I mean a terabyte-ish. Okay. All right. Good. So hopefully this. Do you guys feel like you've solved your big data problem? How to process that data? Does anybody feel like they've solved it? No. No. Because I will tell you what. You know, in any talk that I give, in a room this size, there's somebody in here who's smarter than me. You know, maybe all of you. That's very possible. If you are at the end, you can ask a smart question, and then I'll give you a job offer. So let's talk about what we did. This was our first idea. This is not the one you want to take a picture of. This is our first idea, and I really thought this was going to work. You know, the naivete was very, very strong here. So, but the gist of it is that we had a Kafka queue that was fronted by a RESTful service, and if please don't feel shy. Like if you don't understand something I've said, if you don't know what Kafka is, or you know, feel free to ask because somebody else has the same question. So, you know. What's Kafka? Thank you. Okay, somebody asked the question. So a Kafka is a distributed queue. So it replaces RabbitMQ or a JMS queue or something like that. So a Kafka queue fronted by a RESTful service, I assume most people probably know what that is. And our various systems would make calls to the service with a JSON payload. So what we would do is we would dequeue these using either Spark streaming or our custom ingestion pipeline that we built. Events would land largely unchanged in our Cassandra database. So once they were in Cassandra, we could then use the Spark Cassandra integration to do our analysis straight in Cassandra. And then we would use Spark SQL's ODBC support to serve the data to the various end consumers. So for batch data sources, we would actually repurpose our existing Informatica team to load data straight into Cassandra. So sounded reasonable to me. you know, might sound reasonable to other, I've certainly talked to other people who tried to do similar sorts of things. So let's look at, before we talk about why this didn't work, let's talk about some specifics. Who in here has used Cassandra? Okay, so a few people. Either way, if you've used a relational database, you might have some, this at least should be somewhat familiar looking. So this is what the table looked like that we landed all of our events in Cassandra in. Okay, so the primary thing that we care about here is the event data. Everything else is basically just metadata. And in that event data was a string with schemaless JSON. And then we partition the data across the cluster by the type of event and the time bucket. So this is how we got distribution around the Cassandra cluster. And then we used the new date-tiered, and new at the time, date-tiered compaction strategy, which if you're not a Cassandra person, you may not have any idea what that means. It's basically how Cassandra takes the data as you write it, and because it's all immutable, it writes a whole bunch of files, takes it, groups them into similar files so that read access is reasonable. So that's what it does. So we used that date-tiered compaction strategy with almost no operational experience. So I'd, at this point, had 5 years of operational experience with Cassandra, 0 with date-tiered compaction, and I threw caution to the wind. I thought Spotify created it, they use it, it's got to be good enough for them, it's good enough for us. Then I had a conversation with a guy at Spotify later and realized that's not actually true. So to the TLDR version of this is that that Cassandra was everywhere. So that's what we were using, and probably in complete honesty was somewhat bias from my past, and so that's the direction that we were going, and that streaming data would come in via our custom ingestion process. And we'd use Kafka backed by a RESTful service, batch data via Informatica, Spark SQL via ODBC, and schemaless JSON event payload. And then we would use date-tiered compaction. That would make quick work of our SS tables under the hood. Except that it didn't work. So let's talk about why it didn't work. And the only reason I go through the part that didn't work is 2 things. One is, you know, even big companies with, and we have a very, very talented group of people who know a lot about these technologies, and we still failed the first time, very, very dramatically. And so failure is just part of the process. And second is, if you had any temptation to go down this route, now you won't. So let's talk about some lessons learned from this approach. So first of all, batch loading many terabytes of data every day into Cassandra turned out to be pretty stupid and very, very expensive. And the reason for this is because we were going to need huge numbers of nodes. It had nothing to do with Cassandra. Cassandra could do it. It's simply an issue of the number of nodes, and our number of AWS instances would have broken the bank in the process. And using Informatica to do it was pretty much awful. I could spend a whole talk on why not to use Informatica to load your Cassandra database. Basically, I get the question almost every time I talk about this, like, exactly why? Yeah? Exactly why? No.
I want to hear you say exactly why, but do you think that it's less of an issue with Informatica, more of an issue with ETL?
Actually, I think it has everything to do with Informatica, frankly. And we've spent a lot of time with the Informatica team to tell them all the ways in which they screwed up so that they can go fix it. But in the meantime, we've found a different solution.
For humor, is it anything to do with their IBM acquisition?
No, it doesn't have anything to do with the IBM acquisition. But the fundamental problem with Informatica is that they completely misunderstood their connector to Cassandra, completely misunderstood the nature of Cassandra, how it works, how distributed database works, and was completely naive. So it treated it like an ODBC source, as if it were a single data source, a single machine. So for reasons I'll explain in a minute too, we found that we didn't actually need to maintain this RESTful queue, this RESTful service backed by a queue. And that actually had added significant cost and complexity to the system. And one of the most difficult issues, who uses Hive? You guys, Hadoop people use Hive? Okay, so Hive, just so that you know what Hive is a query engine on top of Hadoop. is essentially what it is. And Hive has become sort of a standard for running SQL queries over big data. So even if you're not using Hive, like Spark SQL is Hive compliant. So one of the most difficult issues we encountered was actually the lack of an open source Hive driver for Cassandra. And we needed this in order to support Spark SQL queries against Cassandra. So if you use the DataStax enterprise version of Cassandra, the one you pay for, we don't like to pay for things. If you use the one that you pay for, you actually get this. So if you happen to be in that camp, then you get it for free. There's also an open source project called Cache, which I happen to have been the very last contributor to over 2 years ago. And so it's old, and we decided, do we want to bring that in and support it, or do we want to just go a different route? And ultimately, we decided to go a different route. Date-tiered compaction we found is broken. Just bluntly, it does not work as advertised, and it come to find out after speaking with a bunch of people in the community, no one had actually run it in production. And so, it was somebody's research project, and if I'd done a little bit of digging, I probably could have found that out. And somebody's master's thesis was date-tiered compaction, and through a string of strange events, it got merged into the code base with no testing. And so we tested it. And you can check out you can Google that and check out the ticket number if you really want to dive into that. I could also do a whole talk on that. So the other thing that seems super, super obvious after the fact is that schemaless is bad. And so why is schemaless bad? Because you must parse the JSON every time you want to use it. So on initial read, you have to parse all the JSON, right? It's expensive to analyze by event type because it's embedded inside the JSON.
By key, are you meaning the key of
No, I mean
record,
important. By key, I mean important. And you can't tune by event type in this case either. So I can't say, since all my data is going into one table, I can't say, well, okay, this data set, this event type is particularly heavy load, and this one's lighter, and this one has this characteristics, and those sort of things. So I can't tune my ingestion and table parameters and those sorts of things for each event. All of which seems stupidly obvious now, but at the time, we thought schemaless great. So here's our take 2, right? This is the one if you're taking pictures, you'll want to take a picture.
So how long did it took you to build the failed architecture and realize that?
It took us much less time to build it than it did for it to fail. Because we stitched together, we had a lot of experience with most of those technologies. It's just the way we stitched them together that didn't seem to work properly. And specifically, it took us probably a couple of months. It was really, so the ingestion part, we started with ingestion, as do most projects. You're just bringing data in. And it wasn't until we started trying to analyze it. So it happened to be a confluence of events of the fact that date-tiered compaction takes time to break, as in quite a bit of time. And it's not until you start reading the data that it breaks. And so, we found that writing the data was perfectly fine for a couple of months. We could write till the cows come home, and it was not a problem. Once we started reading the data, we ran into the broken date-tiered compaction and the issue of having to parse this JSON every time we wanted to do anything. So
where's your JSON parser?
So now the JSON parsing. Actually, I'm going to get to that. So let me arrive at that. So basically, in this architecture, we replaced Kafka with Amazon SQS. We run in Amazon, and I'll talk a little bit about specifically. So this is kind of the high level, and then I'll dive into each of these in detail.
What was the time frame in calendar time when this?
So the very first architecture went into place last April, maybe, so about a year ago, and then it took us maybe 2 months or so to realize that this was not going to work. And somewhere mid last summer, we had a major crisis, lost all of our data, was a serious problem. So mainly because of date-tiered compaction. And again, If you want to ask me about like exactly why we lost the data and why we couldn't recover it, I can talk to you a lot about that. It has mostly to do with broken date-tiered compaction and how it created the way it created files and how we couldn't recover with those files that were created. But the bottom line is that, so it was a couple of months, and then it took us about a month to fix the broken Cassandra bugs, because this isn't the only thing that was broken, and we worked to fix some broken bugs. So there was a confluence of difficult events, a couple of bad Cassandra releases, date-tiered compaction, a broken architecture that really gave us a month or so of hell about last summer. And then once we got kind of out of that, and we were able to recover. So
your first solution, so you've been working for a while?
it did.
And then once it started becoming apparent it wasn't, then
Yes.
you started to scramble.
Yes.
How much administrative or executive pressure did you get to just like fix what it was as it was, as opposed to like uproot big chunks and like replace them?
So I would say we were, I'd love to give you the answer you're probably hoping for, which is a lot of executive pressure. But the reality was, at this point in time in the project, it was a science project. And so while we had a significant amount of data that we as a team did not want to lose because we wanted to use the data, it was more of, you know, we didn't have it before we started. So it wasn't like we came in and ripped out a production system, put something in that was then the cause of a bunch of data loss that was very visible. So, you know, this was somewhat, we were still in our dev cycle, and it just caused us not to hit our dates, is really what happened.
All right, guys, any more questions? Let's save it to the end.
Okay. Okay. All right, so how are we doing on time? Do we have a specific, by the way, do we have a specific timeline you're trying to keep to?
We usually do like 8:15. We're pretty like.
Okay, well then I will hurry up.
And for questions, so you guys will have plenty of time to ask questions.
Okay.
But don't feel rushed.
Okay. All right.
No pressure, just 5 minutes. That's all.
No pressure. Okay, and Ina's coming after me, and I want to make sure we get to her stuff, because that's more. What's that?
As in any dev project.
That's right. We're behind schedule. Is there executive pressure to meet a time? Okay, I'm going to stop joking and talking. So bottom line is, this is our architecture. We moved away from Cassandra for everything and towards S3 and Parquet for a data lake. We used Informatica only to populate our long-term storage in batch. And all of our streaming analytics go, again, through Spark Streaming and the custom ingestion pipeline. There's actually some stuff that's changed in that since this diagram, but it's probably not worth mentioning for this, for your purposes. So let's talk specifically about the data model. So each event gets its own table. This allows us on the converse to to tune individually based on workload. It's very important in Cassandra. Schema is applied at ingestion. So to your question about the JSON parsing, our custom ingestion pipeline actually does the JSON parsing. There are a number of reasons for this. A, we're reading it anyway. So it's got to be read and written somewhere. So the logical place is you might as well, if you're going to read all the data, you might as well actually go ahead and parse it. And actually we break out all the columns. We write them into actual database columns. So each schema, each table schema is tailor-made for that, that actual event schema. This obviously makes subsequent analysis substantially easier and allows us to filter junk early too. So as you may know, if you've dealt with any sort of streaming large data set, even small data sets, you get a heck of a lot of junk. And so this allows us to just go ahead and put some filters into our mechanism since we're reading the data and just go ahead and kick it out. So, to sort of summarize, we use Cassandra for streaming data. This is a rolling time window. So instead of storing everything now, we actually TTL the data, which just means we apply an expiration and then Cassandra kicks it out for us. This gives us real-time access to events, so the time window we can see data as it comes in, but it also keeps the cluster size reasonable. Right now, just to give you a sense, we're running 30 nodes, probably going to scale up to about 150 Cassandra nodes, each of which stores about 3 terabytes of data, and has 128 gigs of RAM and 16 cores. So we have about 30 of those machines right now, and we're in the process of scaling that up to 150 to handle some additional workload. So we keep about 30-ish terabytes of data hot in that rolling time window at any given point in time. So data locality, when you're dealing with Cassandra, it supports data locality with Spark and Hadoop and those sorts of things. This actually makes jobs a lot faster. And then we throw everything else into S3. So the data goes from Cassandra through Spark jobs that every night, or actually not necessarily nightly, but on some time window, grab the data and drop it in Parquet and S3. And so this primarily consists of our batch data loads, our daily or sometimes hourly or minutely Cassandra backups, and then they're all stored as Parquet. The great thing about this is if you don't know about Parquet, you should go Google it and read the Apache documentation about Parquet. It basically allows for efficient, it's essentially like a whole bunch of small relational databases in terms of structure, and allows for efficient parallel queries into precisely the data you want to extract. So we do that. And then this gives us cheap, scalable, long-term storage in S3, as opposed to having to pay for instances in Amazon to run, our very expensive instances for Cassandra and Spark. And also, Parquet and S3 are both natively supported in Spark, so that helps us. And then the other great thing about it, maybe the best thing about S3, is that we can share it. So if we have a data set that we want to share with other parts of the company, or other parts of external customers, or have external customers or business partners drop data into our data lake, we can just give them S3 credentials, they can drop it right in, and then we read it right out. And there's also open source Hive support for through HDFS, the HDFS S3 connector. So Kafka was replaced by SQS, and the reason for this is that it's scalable and reliable. Not that Kafka isn't scalable and reliable, but SQS also is. And it's already fronted by a RESTful interface. If you've used SQS or any of the Amazon services, there's a RESTful interface to everything. And that's the same thing for the SQS service. And that's simple queue service, in case I didn't say that. It's nearly free to operate. We're actually the largest SQS user in Amazon. And so, but it's still, even then, nearly free for us to operate. On the order of tens of thousands per month at our level, which is pretty substantially cheaper than running a whole bunch of Kafka machines. And it's also got a robust security model that fits into all of our other AWS security. And to do this, we do basically one queue per event type per platform. And then that's kind of the structure and the sharding that we do for queues. And it also has built-in monitoring. So all these things that we would have had to stand up, and run, we now don't have to run that in infrastructure. So date-tiered compaction was replaced by an experimental time window compaction. So if we wanted to be, we went from experimental to super experimental, but we did a lot of testing first. And this is actually something we were about to write, and then one of my compatriots in the Cassandra community messaged me and said, hey, I got this cool thing I wrote. You want to try it? And we tried it, and it works brilliantly. And now I'm lobbying hard for it to be the replacement for date-tiered compaction in Cassandra core. We'll see how that goes. Developed, blah, blah, blah. You don't care about who developed it. The bottom line is that it groups data by similar timestamps and expirations. And so then when the data is done, it just deletes it from disk. So there's no compaction overhead for getting rid of TTL data. And it actually improved our stability and throughput substantially. So overall, this was awesomeness. So fine print, you can read this later. I'll share the slides. Actually, if you Google this talk, I gave it at Spark Summit and Cassandra Summit, same talk, and took a little bit longer and went into some more depth on some stuff. And you can find the slides in the video. So also fine print, if you're going to use Spark and Cassandra, make sure you use the versions in the SBT file, which is the same as like a Maven file if you're not a Scala person. So some more fine print. We actually use more than one Spark cluster. We use co-located Spark cluster with Cassandra for heavy analysis. This gives us predictable load and efficient Cassandra access. And then we have a self-serve cluster, and actually, as we're moving towards multiple self-serve clusters that are spun up on demand. And this helps us deal with unpredictable load, things like self-serve queries, mining S3 data, people coming in, data scientist Ina, if Ina decides to run an expensive job and breaks the cluster, she doesn't break the production Spark cluster, she breaks the, a special one that we've set up for her. So basically isolation from production jobs is what that buys us. So a little bit of data modeling. So I want to probably blow through this quickly unless you guys have specific questions in the interest of time. But in many ways, if you're familiar with, so who's done data modeling on a distributed database? Like Cassandra, HBase, anything like that. So you're probably, if you have done this, you're probably familiar with the idea of writing your data in such a way that it only hits a single node when you want to ask a question of that data. So partitioning for analytics is exactly the opposite of that. You don't want a Spark job that's a distributed system to be running if you had 30 machines running Spark and they all had a single table on a single node for all of its data for a query, then you've got a problem because that's your bottleneck. So you actually want to reverse the modeling, and you want to have good distribution for your queries instead. So you model for good parallelism, not for single partition queries is the bottom line. And this works whether you're using Cassandra or HBase or any other distributed database. If you don't do this, like I said, you're going to end up with a lock, essentially lock contention on that single node. So you do want to avoid shuffling. Anyone who's used Hadoop knows that shuffling is the most expensive part of any distributed processing job. And basically shuffling occurs when you are not grouping by your partition key. So what this means is I go out and read a bunch of data from a bunch of different nodes, I bring it back in, and in order to say, let's say it's all partitioned by user ID, and then I want to group it by location. So I'm going to bring it all back in, I'm going to have to shuffle it all around and regroup it by location, ship it all back to my individual nodes and shuffle it around and then do the processing. That's super expensive. So that's what you try to avoid. So you want to partition, this is probably the most important thing, like if you fell asleep, you're going to wake up, read that one statement, go back to sleep, and wait for Ina. Partition for your most common grouping. That's like data, distributed data analysis 101. Partition for your most common grouping. Otherwise, your jobs are going to be really expensive. So also secondary indexes are very useful. Conventional wisdom says don't use them for operational use cases because they involve essentially a distributed query. But in this case, distributed query is exactly what you want. So they're very useful for database level filtering. Reduces the Spark workload and the RAM footprint for your jobs. Low cardinality is still the rule. So just a quick sort of substitute Cassandra for your favorite database. You're going to hit, if you do a secondary index with a normal sort of application access model, you're going to hit a coordinator, whatever node is that's handling the query. It's going to go out to all the nodes, query the index, aggregate the results, and bring them back. With Spark, it's very nice because you got this nice distribution. Spark is able to query the local index and use index only for filtering. So you can also do full text indexes with Cassandra in case you're interested, for the Cassandra people in the room, using a Stradio Lucene plugin that gives you Lucene capabilities on Cassandra. So I'm going to kind of move past some of this stuff. Other thing, really important, probably the second most important, maybe the first most important, I don't know, you take your pick. So I think I said I only had one impressive slide in the deck, and it was the first one with the storm that's now everywhere on LinkedIn. But this one is actually my second most impressive slide. And the reason that I put this up there is because this is the other thing that will literally kill you in a distributed analytics job. So what is a wide row? Anyone in the room been killed by wide rows? Am I the only one? I'm the only one. Okay, well, your time is coming. So what is a wide row? So a wide row is basically in a distributed database. So I'll give you a concrete example. We had an Android client is writing a bunch of data. I won't say what kind of data, but writing a bunch of data. And it was supposed to be anonymous. And they had this scheme for creating keys when the data was anonymous to replace the user ID. Well, their scheme broke in a release, and it became anon colon. So we were getting tens of thousands of inserts per second with the same key. Now, in a distributed database where the key is the unit of distribution, what we ended up with is, and a replication factor of 3, so replicated twice in 2 other places. What we found, what happened very, very quickly is it overwhelmed 3 nodes out of our cluster and was taking them down. And we just, we couldn't figure out what was happening. They were going down over and over and over again. We tried to, try to figure out what was going on, and we couldn't get the data off of them. It was a big mess. So it only takes 1 to ruin your day, is the bottom line there. These are Cassandra-specific stuff. I'll let you come back and see the slides if you're interested. Another important thing, if you're using Cassandra or most other distributed databases, there's nulls or deletes. Don't write nulls. So just leave it at that. They complicate your whole system. So I will not go through all of that. Quickly, data exploration, really important if you want to shorten the life cycle from the time you ingest data to the time you can get insights from it. Your ability to explore it and visualize it is important. This is an old paradigm for how we did that, right? Getting the data through the system, involving DBAs and all sorts of stuff. Now, this is the new paradigm. We visualize at every step. So how do we do this? So first of all, it's critical to understanding because a human brain can't make sense of terabytes of JSON. It just can't. We've got to do something so we can plot graphs and look at charts and do those sorts of things very early in the process. And again, reduce time to visualization. And previously it was taking us, tools like MicroStrategy and these sorts of things that involve creating models and all this sort of stuff before you get to visualization. It's going to be months or more. We wanted to take that down to, I got a new data set, I want to visualize right now. That's the objective. So it also takes your process, your data process, from a waterfall process to an agile process, which is pretty important if agile is all the rage I hear. So we actually chose in order to a tool set in order to accomplish this called Zeppelin, and since we've introduced another one called Jupyter, which you may be familiar with. So it's an open source Spark notebook, has interpreters for a bunch of different things, and allows you to produce data visualizations and go straight from data visualizations to scheduled jobs very quickly. So for example, this is a little SQL query, and underneath that SQL query is a bunch of JSON. So pretty awesome. Here's a Scala example of how I took some data that was in very raw form, did a little bit of pre-processing on it, and then created a temporary table, and then did a select from the table and produced a graph, taking some temperature data from different locations and plotting it with dew point. You can also just do straight queries against databases if you want to. So other stuff that we plan to do in the future, we want to actually remove Cassandra. So this is, I'm going to skip past some of this stuff. The bottom line is ultimately we want to go straight to Parquet. We want to skip Cassandra as a temporary storage, and there's work involved in doing that. It's not possible right now, but we're working on that. And then, so that'll eliminate the interim storage. That's currently in R&D. And so the third most important slide here is we are hiring. So in the interest of, and we're hiring data scientists, data engineers, visualization people, project managers, everything. If there's anything having to do with big data analytics, we're hiring. So, with that, I'm going to, unless there's like a burning question, maybe I'll take 1 or 2. I'm going to let Ina talk because it is like burning on fire time now.
Question from sales guy is okay?
What's that?
Question from sales guy is okay. Question from sales guy is okay.
Okay.
Is going to be
Go
basic.
for it.
So the architecture slide.
So the architecture slide, which you've shown on the architecture 1, you had
Yes.
an ETL layer.
Yes.
So my question, the data goes to the lake and the raw storage. Why actually you need that ETL there? Can we put that ETL above the data lake, like when you want to visualize, so will it not increase the speed? When you're putting it into a raw storage or to a lake, Okay. By the way, my knowledge
okay.
is very,
That's okay.
basic. So please forgive me. But do you really need an ETL there? Can you put the ETL somewhere else rather than you putting into a raw storage? Does it not increase?
So I don't know where else we'd put it. ETL does a variety of things. It takes.
I understand what is ETL. So
Yeah.
You're putting it into a raw storage. When your data source is coming and you're putting it into a raw storage, can't we put the same data into the raw storage and into the lake? And when we're trying to make use of the data,
just keep in mind that raw storage and data lake is physically it's the same thing.
I understand.
So
let me relate it to you something. What is told. You told about what is the earlier paradigm of the warehouse looks like and the new thing. So I'm trying to relate that to your architecture. So your architecture and that is not actually matching because it still goes to the
ETL layer. In the first iteration, it wrote to Cassandra.
Yeah, even
in the second iteration, it writes to raw storage and Parquet and S3.
So that's what my question is. I don't know. Okay.
So it's a completely different architecture of the target. The target of the data is completely different. And actually, just as a side note, we're trying to move away from batch as much as possible and move everything. Think about everything in terms of streaming, and so that's actually the evolution we're moving towards. Yeah.
I like your slide that said pass.
Thank you. Compliment.
If you would, what company are you in with 360 petabytes of data, and were they having similar problems with Cassandra and working data, or?
It's very small company. In fact, we find that a lot of things we have to build ourselves. We have to, so we have a lot of people. In fact, my entire team, 30, 40 people is focused on infrastructure. So most companies don't have that many people focused on infrastructure. So that's the reason that I'm up here talking about infrastructure is because that's a big problem for us. Most people can get away with things that we can't get away with. I like to say simple problems become, easy problems become really complicated and interesting at scale. So
your early question about how much data you're working with is very significant to this.
It is, but I will say this architecture works for, it scales up and down. So if you want to build a Lambda architecture where you're doing event processing, those sorts of things, the great thing about this architecture is you can start small with it, and then it can grow as big as you need it to. So, all right, with that, we'll get to who you really came to see, which was Ina.
So hello, everyone. I'm very happy to present to you today. It's an exciting opportunity, I think, for both of us to get exposed to so many data scientists and people who are interested in data science. And, my work is to get data sets from what these guys are collecting and make sense out of them. And one of the data sets that I've been working with is our location data. And the location data is pretty much the GPS locations that we track from our mobile users. Right, and the name of the project is Predictive Weather Alerts. Is it about weather? It's a little bit about weather, but not. It's mostly about our users. All right, so how many of you have any experience with our mobile applications? Okay, quite a few. Oh, great. That's amazing, actually. And how many of you have used push notifications for the weather alerts? All right, great. All right, so if you don't know about it, our app has a nice opportunity for everybody to get different kind of severe weather notification or lightning notifications or rain and snow notifications that are pretty much real-time data for your location. For instance, if there is a rain in like 15 minutes, you're gonna know about it. You're gonna make your plans according to that, right? So what we wanted to do with this is to go further and to be able to predict the user location and provide the information ahead of time for the location where this user might likely to be in the future. So this is not the actual forecast. Just ignore it. This is maybe in some parallel universe. All right. So, but imagine you have so there is a person who lives somewhere in this Stone Mountain area and goes to work in the Smyrna area, and this is where the Weather Channel is located, by the way. So for this, you might think of like a regular pattern. In the morning, you go to work. At the evening time, you come back. So you have like time slots where you in one location and another time slots when you're in the other location, right? Saturday, Sunday, you may have all the different plans. You can go anywhere, right? So the mobility patterns for a single user stay pretty stable over time. That's what we wanted to study and to understand how we can send you the forecast for your location where it's rainy tomorrow at 8 a.m. while you're having dinner at home over here in Stone Mountain area. All right? So for this, we designed the predictive model for every user, and it pretty much contains 3 major steps. So the first step is modeling. And modeling involves machine learning algorithms, and I'm going to talk about it further, but the whole process starts from getting the data, the location data from Parquet files. Then we process it in Spark for every user, and we have millions of users, so it automatically becomes a big data problem. We derive the model for each user, and we store it on S3. So we store it back on S3, right? So when we want to actually predict the next the location for a particular time, we retrieve these models from S3, and we process, we make the prediction, and then we can basically aggregate users by their locations into like these blocks of areas, all right? And store it back to Cassandra. And then if there is something going on with this location, so if there is like the rain is coming or tornado is coming, you can send the notifications only to users who are going to be in that particular location. All right, so it goes to the product type. And this is our, like the app, if you don't have experience with it, so it sends this nice notifications if there is a weather change. Okay, so I want to introduce one of the terms I'm going to use in the future, and this is the geohash. So the geohash is pretty much the hierarchical spatial data structure. Okay, so over here you can see, for instance, we have a block on the map, which is pretty much some area on the map. And it has the unique identifier. It's Greek based, so this is 2. If we want to scale in and get more precisions, it gets 1 extra character, and so on and so forth. So pretty much you can split all the, you can split map into these blocks, and they can be as precise as you want. And these identifiers are unique, which is also important for the aggregation purposes. And for our case, we use the geohash of precision of 5. So and it gives you 4.9 by 4.9 kilometer blocks, which is pretty good size for the weather forecast, right? Like 5 by 5 kilometers, like pretty much like 2 by 2 miles. But to start with, as Robbie was talking about, we need to do some descriptive analytics and to see and visualize and see what our patterns may look like. So over here, I have the mobility pattern of a single person. This is just an example, and each color represents a location, and each bar, like this long bar, represents a day. If you can see it from 12 a.m. to next day 12 a.m., right? And it's about for the month's worth of data. And from the slide, you can easily see that this person spends like time slots in the middle of the day in a specific location, and all other, like some of the other times in different locations. But he starts and ends his day in pretty much in the same location. All right? So with that, we derive the entropy by regularity. And entropy by regularity is the characteristic of a personal mobility pattern. And well, there are two types that you can think of. First, entropy by location. And entropy becomes higher if a person has more locations. And, but regularity is more precise way to measure entropy, because it's not only cares about number of locations. It actually doesn't care about number of locations that much. But it allows you to understand how regular this person is. For instance, if I have 5 locations, different location, homework, and let's say 3 points of interest I go, but I go in all different times. Whenever I want, I go there. I'm not so regular in this sense. But for the person who has 15 or even like 20 locations, but he always goes there in a particular in a particular times, this is the regular person. So you can always say, oh, this person in that location today, and tomorrow he's going to be there. All right? So this is just some examples of the 3 types of location: the regular mobility, normal mobility, and random mobility. However, number of locations affect entropy, as we understood, greatly. So you can see the distribution here. And on the first slide, this is the number of locations and number of users that have this location for this sample of data. And on the second slide is the entropy by regularity and number of users who have it. So the 2 charts are pretty similar. For the modeling of the mobility pattern, our goal was to make a predictive model for every user to achieve the better user experience and personalization purpose. And as an input data, we used 2 months of location data. And because there was some well, we did it in parallel with the engineering team, so that's why sometimes there were some discrepancies in data. So I was trying to kind of get all the possible data I could get in that time, and it was last summer, so the process Cassandra kind of, yeah, Cassandra issues the here and there, but you know, you're like a data scientist, you need to like take advantage of what you have. And as a columns, we retrieve only user ID, timestamp, and latitude and longitude. Okay. So the next step was ensure that data has a good quality. So the data quality control is one of the, I would say, the crucial part of modeling process, because if you have bad data, you're going to get bad results most of the time. So the data quality control includes included resampling. Basically, you resample your data by 10 minutes time frames to reduce noise, and sometimes device could send like multiple locations in the same time, or it could be like a big interval between the location. Just to ensure that it's a good time series data, you resample it by some interval. And the second part is to extract the date feature from the timestamp. So you could understand how many days worth of data this person has. And well, because you don't have anything but date and user ID and the location, and somehow you need to predict the location, you need to generate extra features. And in this case, we added time, which was just an integer, number of hours plus number of minutes in minutes. Weekday, which was also an integer from 0 to 6. And weekday could affect the mobility pattern because well, on weekends you don't go to work. Most of you, I hope. So another one is the if this day is a holiday or not, which is also affects. And the geohash was pretty much derived from the lat long, right? And geohash is gonna become our label in the future for prediction. Okay, the random forest model that we built for every user. How many of you work with machine learning? Like a lot of people work machine learning. A lot of people know about random forest, why it's good, why it's not. So we evaluated a few models, and the best were random forest, k-nearest neighbor, and decision tree. So I didn't like decision tree because it usually overfeeds, and in this case it tried to overfeed data. That's why it was probably the good performance. And also it doesn't work well on generalized data. For the k-nearest neighbor, the problem was that you have to carry this model with you around. And for nearest neighbor, the model itself is big. So because we need to retrieve model from S3 quite often, k-nearest neighbor is not the best approach because these operations can take long time. So what we did, so for the random forest, what it does, it produces a lot of weak decision trees, and it takes random features and random samples. So it creates a good random subset of data, and train the variety of decision trees. All right, and the output then calculated by the by some of the aggregation function. Well, it could be anything because decision trees used for classifications and the regression. So in total, it doesn't overfit that much, and it works good for the generalization. So another interesting part about this problem that it's a multi-class classification. Usually, a lot of the classification problems are binary, so it's yes, no. Does this person go there? No. Yes. In our case, we had a lot of geohash location where this person could potentially go. So the problem becomes more advanced in this sense. And for the random forest, the features, as I talked before, became the time, weekday, and holiday. Also, we added the sample weight because the data that are further in the past is less important than the most current data. Okay, so the timestamp was a linear decay. And the label is the geohash. So we were trying to predict a geohash label. As an output, you get the serialized predictive model that is saved on the S3 and can be in the future retrieved and used many times. So that's the same example for the prediction over here, and for the same user. So as you can see, the model pretty much, this is 1 week of data, of the predicted data. You can see that it captures very well the, I would call it like working hours, and also it captures 2 extra locations that users tend to go on a regular basis. So the problem of, I would say most of the machine learning algorithms, that's they're parametrical, and to choose parameters, we use the Greek search. So the Greek search pretty much exhaustively generates candidates from a Greek of parameter values. You pretty much mix all the possible parameters and exhaustively search for the best variant. Well, why we did it? Because I wanted to have the best model, and I thought, well, the random trees don't have so many parameters that could change, and I pretty much know what their values could be, and there is no like continuous values and stuff. But I think two other ones, the random search and genetic and evolutionary algorithms, would work much better in that sense. If you have a model with continuous values and you want to evaluate a lot. In the end, we evaluated the accuracy with the cross-validation. As on this slide, I have relationships between entropy and accuracy. All right, so as you can see, the accuracy goes down as the entropy increases. Of course, for more regular people, it's much easier to predict their locations than for people who just go all over the place. But also, for the random guess, as more places you get, the harder it becomes to guess, because in the binary problem, it's 50%, right? When you flip a coin, it's 50%. In the dice sense, it's 1/6. So in our case, there are going to be many, many more locations, and I think the performance, which is random forest gave us, was much, well, you can see it was better than random guess. So for the prediction, for the second part, we retrieve the our models from S3, and we create the query that consists of 24 hours, and that represents a time series on within an hour frame. And each query is run against this user model, and then the users aggregated by geohash and timestamp and put back to Cassandra. So why Cassandra is good in this case? It doesn't hold the predictions for a long time, so you can update it like on a daily basis, for instance, and remove the ones that are old. And that's pretty much my last slide. And this is about why I like to use Spark and why Spark was so great for this problem. So first of all, Spark has a lot of easy read writes to easy connections to S3, Parquet, Cassandra, like whatever you name it, any kind of data set you want to retrieve, you go back and you don't think about all the other qualities of data set. The problem itself was very easy parallelizable, because we needed to do the model for every user, right? So, and here I have 4 functions that I used to do it. So the whole project was just 4 functions in Spark. First function is to retrieve the Parquet file on S3. The second is to shuffle everything, and the second one is to retrieve the columns that I want from the whole data sets. Next one, to bring all the points that belong to a user together. Right, so because our Parquet files are organized by date, and we wanted to get user ID and all the possible data for 2 months for this date. And the last map function creates a model and save it to S3. Right, so, and just because so many users, just because the parallelizable problem, the load balancing also becomes very easy. So there are 3 E that I call that why we use Spark and why we're going to use Spark in the future. Yeah.
Quick question.
Yeah.
I'm assuming you already had enough historical data to start predicting how people turning on this feature. But what if, let's say, someone just downloaded the app? When would you start to be able to get accurate predictions, you think?
So it could be started as long as we have at least 1 month of data.
Okay, so you need 1 month.
Yeah.
Okay.
So we could start earlier, of course, but then the prediction is not gonna be as good as you can. At least you have 1 month, because it's like 4 continuous weeks. Yeah.
Yeah, great talk. It seems like a lot of the majority of predictions use regularity, but do you also kind of think about using conformity as well? Kind of like similar users might have similar location preferences and doing some sort of collaborative filtering approach?
Well, it could be done, but the purpose of this project in particular is not to focus so much on a specific location, but on the area where this location is, because like by the end of the day, I care about the weather over there, right? So that's why it was more about where this person is going to be, like area-wise instead of like business-wise.
What about demographics as far as this? With that, you can see the behavior of the person based on the information that you get, and this way, sometimes you can do predictive analysis using that.
Right, I agree with that, because the demographic matters. Demographic matters for the purpose of, first of all, for the purpose of the to understand the mobility, right? Because, for instance, people, well, not only about it, but there are some sets of people who are most likely to travel more than others, right? So the demographic can be really easy implemented into extra features over here, and just to see how important it is, evaluate it also can be done. Mm-hmm. Yep.
Just a different question. What is the average distance a user travels in Atlanta, let's say? And what is the delta change in the...
No, that's a secret information. I cannot. that's the weather channel like the weather company internal.
What's the delta change in the users from, let's say, point A to point B? Does it really matter for a user to know the delta change in the weather? Because if you are using level 5, which is 5 by 5 kilometer, and he moves, let's say, 25 kilometer or something like that, what is the delta change in the weather, and does it really matter for him, or is it mainly for you?
Well, it depends on the weather. I mean, it depends which weather we're talking about. Yes?
I was just going to say, I mean, you can imagine, like, if you live in the city of Atlanta versus, like, in Woodstock, the weather patterns are very, very different in those two places in many cases. Tornado watches in one place and not in another, and rain in one place and not in another.
Yeah.
So it's very easy to imagine. It happens all the time.
And Atlanta is the unique place in the sense because we could have like this intermittent rains like quite often. In the middle of the day there's just rains and then there's sun and stuff like that. Yep.
Is this functionality in production now? And I wonder if you can say anything about that process of scaling it up from 11 in development to 11 in production.
So it's not on the product yet, but I can talk about well, probably like it's this scale actually. Well, what do you mean? I just want to understand like the problem.
I mean, I'm imagining that when you're doing the development you described here, you might be working with your laptop or with your laptop. But at some point, this has to be rolled out. Right?
Oh yes. No, the whole project was tested on the actual number of users we have, which is millions.
So is there any further steps then to make it production ready, or is it there now?
I hope.
To easy answer to that question is the data science is ready, the back-end pieces are ready, but there's a lot that goes into testing a feature like this to make sure you're not sending people bogus data. So there's that piece, the product testing part that has to take place before it goes into production. But from a data science and scalability perspective, it's ready.
Yes?
Are you currently able to deliver like watch or warning products to people who are within certain geometric regions? And does this solution contribute to that? I'm thinking, if I'm in a tornado warning polygon,
yeah,
does it? And I'm away from my home. Would I be able to receive the polygon even if I'm in a region away from my home? Am I able to do that with this solution?
So not now. Right now, it's not on the product yet.
But I think your question is, does it plug into that solution? We have a solution right now that is what you're using when you get severe weather alerts, that this plugs right into because it's all geohash based. So.
Plus, I thought those solutions were tied to my home location or some other location that I get.
Yes, but it's still an intersection model. So it takes the polygon and where your home location is and does an intersection on that. You know, so it's 120 million people with all the weather events in the world and an set of intersection logic happening all the time to figure out who we need to send them to. And this is just another point to intersect. So it's the same system that sends out weather alerts regardless.
And I can attest to that because I was in Oklahoma when the tornado hit, and it sent me the warning fast. So it does.
Even though yours was set to Atlanta?
Huh?
Even though your normal.
Yeah, even though it was set, but I was in Oklahoma.
Okay.
Yeah, we keep track of where users are so that we can constantly do that intersection logic.
Yeah, it's more
That's a whole different
time.
product
Yeah.
we could talk about another time.
Yeah. Okay, so on the back, I think. Yeah. Okay.
I know it's not in production yet, but what are some metrics you want to look at to judge the success of this product? So how would you, success criteria, how would you know, like, okay, great, we could do push notifications of weather, but how would you actually know that people are going to look at it and use this?
So it's pretty easy because we have a prediction, right? It's the same as forecast for the weather. You think something is going to happen, and then you get this information next day. So I think the best way is to...
Well, no, that's accuracy. Of course, you're accurate. Your model will be accurate, but it's, is it going to help user experience? Are people...
Well, this is the whole separate topic for the user experience team, right? Who's going to like evaluate the feedback and stuff. Yeah. But I think for me, it's much easier from the point of the like data science to evaluate the accuracy and stuff.
How do you guys make money on this?
By keeping users and getting new users.
No, that's actually it. What she just said. I mean, you know, it's all a retention market share game. You know, we sell ads and data. That's basically what our business sells. And so the more customers we have, the more ads we can sell, and the better data we get to turn around. And for example, we can say things like how we can tell the NFL who, you know, not who, because we don't give any personal information out. But we can say people who came to this football game came from out of town. You know, this percentage of people come from out of town. They spend this number of days on average in town, and then they leave this many days afterwards. They stay in hotels, they go to bars, these sorts of things. Like this is a way to monetize this on the back end, you know, while providing, you know, also simultaneously a feature that is useful for people on the front end.
I was wondering is for when you use Spark, so this sort of ties back to the infrastructure, but if everything's sort of in S3 storage, and I don't know a whole lot about like cloud computing, but I get the impression there's sort of storage nodes and there's compute nodes. But when are you sort of streaming data out of your data lake and processing it separately in like a separate cluster, or is it being done like in memory on the?
So there's some production machine, right, and there is storage. You retrieve data from storage, and then you process it, and then you put it back. Okay. So think of it like the production machine is your processor, right, and the storage is your hard disk. So it just stays there, waits for you to come and read, then it processes, and Spark is like live, I would say, so it's those nodes are running all the time. And then it goes back and puts it. And also the Cassandra nodes are also up on all time. So the Spark is able to put data in Cassandra right away. Right. So Cassandra
and in that case, it's co-located. So the processing and compute are in the same place. I mean, the processing and storage are in the same place.
So the storage of like your scoring model that you can then score.
That's in S3.
Yeah, that's S3. So it just stays there, waits till you retrieve it.
So you had thrown some light on parallelism tuning and how you do that. So this is one of the things which I struggle with. At your scale, probably you cannot apply one set of parameters to all sorts of customers. And so you can broadly classify them by intro to then have a set of parameters for them. So that's one of the questions. Do you do that?
Yes, yes.
And the other question is, if you do that, do you have an automated mechanism to reset these parameters on a regular basis, or is this a monthly evaluation or a bi-monthly evaluation? What's your take on that at the scale at which you operate?
Right. So the approach is the following. We divide all users into 3 groups based on the entropy, and for each one we search for the best parameters. All right. So this is like 3. It's not like really like 3 models running, but it's based on the entropy. You can have like a decision tree deeper or like wider or something like that. And the random forest also can have like more or less decision trees just to speed up and balance the process. Because for people with who are regular, you don't need to have like complicated trees and stuff like that. Yeah, but it's done on the subset before you actually run on all the users. Because
it's done every time you run a job, or is that done once and then you run the job for the next 15 days and then you reset?
So the parameter setup runs once. The entropy is recalculated like every time you run the model. Like not when you run the model, when you create the model, right? When you train a model. So based on your entropy, you get into one of the 3 parameters.
I'm sorry, I'm not
Yeah.
So if I'm a single user,
Yes.
and you have a set of data, and I was categorized as a regular entropy.
Yeah.
When am I? And then suddenly I start traveling all over the world. When does that show up in your model? When would I change?
So next time we retrain the model.
Right, and how often does that happen?
It doesn't happen very often now because it's not the product wise. Yeah. But it should be like, I understand. Yeah, I understand what you're saying, and it should be done on a regular basis, just to adjust, because yes, people might change in a sense. Yeah.
3 more questions.
Oh yeah.
What's the most interesting challenge you call it working on?
People.
She's having a baby.
Yes, so I think when you say people, like for instance, like for the patterns, you can say like, all right, so a lot of people have similar patterns going, like you could say, right, like homework and something else. But when you actually deep down and look at what people do, we all do different things. Yeah. So we're all similar in a sense, and we're all different from the things we like. Yeah.
Is that causing you to rethink your strategy?
The future plans? Well, I do not know. Maybe when it becomes more precise, predictive modeling, like for instance, not the only predictive modeling, but also the descriptive analytics. When you start talking about user like particular locations, like points of interest, that would affect that. Like in this case, users could get different relationships between each other based on their preferences. So it's going to be a different type of clustering and aggregation of users.
Do you validate your prediction versus the direction of the people go? So if you are going to predict me, then I'm going to perimeter. And actually I'm not going to perimeter, I'm going to stone mountain. Because based on your model, you're going to say, you're predicting to go to perimeter. So you send me the alert for perimeter.
Yeah.
Do you validate that alert versus my final destination?
So it's done as the part of validation of the model based on the historical data, but we don't do it, so that's the accuracy slide, right? So
the model doesn't refeed itself. Right?
It would retrain, but it would take like in consideration like all the data points that you have. For instance, one day you go there and another day you go somewhere else, it might not catch the pattern because that's not really a pattern.
So
but
Low latency events out of the question.
Yes. In this case, is as good as could get based on the pattern, right? However, because I had the limited amount of data, like 2 months, we didn't include like other things like seasonality and stuff. Like, for instance, because if you just take the single like Christmas, right? People go to specific places, to vacations. They just travel in general, right? More. So it could be also included in the model as the data set grows.
Sorry, I'm really interested in this. So the random mobility, was that actually a more sparse class compared to the others? And did you think about, or were they all fairly, there's 3 classes of people, regular mobility, normal, and random. Were they all well represented in your data set, or did you have to, like, I guess, what is it, jackknifing, the more sparser class when you're training your model on things?
So yeah, it's pretty much the 30-40-30 representation, like 30% of regular people, 40%, like more or less 40% of, okay, so the low mobility is 30, then the regular one, and then the high mobility is another 30%. Okay, all right, so, yeah.
How far out is your expectation for sending the alert versus the anticipated weather event? Like, what sort of time difference? 10 minutes, 15?
I guess it depends on the forecast.
Yeah.
And yes, so as we get the forecast, we could start like predicting the locations and sending alerts.
And it varies on the type of weather condition, because if you're talking about a particularly hot day or a particularly windy area or something like that, like there are places where if you're in a mountainous area, the wind may be high at the bottom of the mountain and on one side of the mountain and not on the other, and so you may send a wind alert a day in advance, but you may send a tornado alert an hour in advance. So it just depends on the weather phenomenon.
I was thinking more locally, like storms coming in from Alabama. Usually I would guess I would predict that.
So it's specifically, just to answer the last question, specifically the way the algorithm works for sending out weather alerts is it says for an event like that, you got a squall line moving through or something like that, and you're going to have something that's really big on its way. What we would do is we would say, okay, look at the forecast for this spot of Earth. And we have a very, very granular, a very interesting topic is how we do forecasting too, because it's very unique in the industry. But I can say for this latitude, longitude specifically, what is the forecast? And so what we can do is we can say, for this, like as the storm is tracking, we can look out ahead of it and say, look at the latitude, longitude 10 miles out and say, who is going to be in that spot? Compute the geohash for it. Who is going to be in that spot at the time this weather phenomenon is forecast to be there? And then do an intersection with all the people from her logic and send out a weather alert. Makes sense?
Yeah, so that was the anticipated.
It depends on the,
speed of the front. But can you just generally say kind of what's your hope in terms of forewarning?
I mean, I think you're getting into meteorological science that's actually much more complicated than you think it is. So the weather alerts we send now are based on a lot of different the variables, how much time in advance we send them. So.
And they're not done in real time?
No, they're done. The weather alerts are done in real time, but we're talking about forecast alerts, things that we know you're going to be somewhere, not where you are right now. Where you are right now is easy. So, well, it's not easy, but it's easier.
So, we'd like to give Ina and Lavi a round of applause.